Hello, young chemists. Ever wondered how we turn simple aromatic amines into something super reactive and exciting? Well, buckle up, because today we start with diazonium salts. Here's a little joke. Why did the benzene ring go to therapy? Because it couldn't handle getting substituted all the time. Diazonium salts are organic compounds that contain a special functional group. Think of it as our N double positive 2, balanced by an anion like chloride or bromide. Here, R represents an aryl group, which is basically a fancy name for an aromatic ring, and X is the negative ion that balances the charge. These salts aren't just chemical curiosities, they're essential players in making azo dyes, aromatic amines, and phenols, which you'll see used in fabrics, medicines, and dyes. Now, how do we get them? Typically, by reacting primary aromatic amines with nitrous acid, and here's the catch, we must keep the temperature low, around 0 to 5 degrees Celsius. Why? Because these compounds are a bit moody, they become unstable if it gets warmer and break down quickly. So, they prefer to live only in the lab, under controlled conditions, acting as fleeting but vital intermediates in synthesis. Picture a diazonium salt molecule, the nitrogen cation attached to the aromatic ring, balanced by a counter ion, waiting to jump into the next reaction. That's our starting point for some very cool chemistry. Alright, moving on. To make diazonium salts, we need the magic ingredient, nitrous acid. But plot twist, it's super unstable and impossible to store. So, chemists get clever and make nitrous acid on the spot, known as in situ generation, by mixing sodium nitrite with a mineral acid like hydrochloric acid. The reaction goes like this. Sodium nitrite plus hydrochloric acid gives us nitrous acid plus sodium chloride. Now, here's the fun part. This nitrous acid has to be freshly made and kept ice cold, around 0 to 5 degrees Celsius or 273 to 278 Kelvin, to keep our diazonium intermediate happy and stable. If it warms up, the diazonium salt breaks down, which is like an uninvited party crasher. Phenols start forming, and nitrogen gas escapes like a balloon popping. Imagine a flowchart that shows sodium nitrite mixing with acid, leading to freshly made nitrous acid, then reacting with the aromatic amine to make our diazonium salt, right in a cooling bath, keeping everything chill. That's the secret recipe to keep the chemistry cool and controlled. Now let's see what's cooking at the molecular level. Aromatic primary amines, those ARNH guys, react with nitrous acid and an acid source HX to give diazonium salts. The general equation is aromatic amine plus sodium nitrite plus twice the amount of acid HX results in an aromatic diazonium ion plus sodium halide and water. Don't worry, here ARNH to plus nano to plus 2 HX gives ARN to plus X plus NaX plus 2 H2O. Read aloud as aromatic amine plus sodium nitrite plus 2 equivalents of acid yields aromatic diazonium salt plus sodium halide plus 2 waters. The secret agent here is the nitrosonium ion, a positively charged species that acts like a chemical superhero attacking the amino group on the aromatic ring to form the diazonium ion. What makes these salts so stable is resonance in the aromatic ring, kind of like how a group project shares all the work evenly. That's why aryl diazonium salts are much more stable than their aliphatic counterparts that lack such aromatic backup. Picture the reaction mechanism as a stepwise dance with the nitrosonium ion approaching the lone pair on nitrogen, forming intermediates, and finally giving us that diazonium ion ready for further chemistry action. Chemistry is like a well-choreographed dance, isn't it? Okay, here's where things get a little dramatic. Temperature and pH decide the fate of our diazonium salts. The best temperature is chilling at 0 to 5 degrees Celsius, much like how we like our ice cream. If the temperature rises, the diazonium salts start decomposing, releasing nitrogen gas and spoiling the party. The acidic medium isn't just for show. The hydrogen ions catalyze the formation of that all-important nitrosonium ion, helping the reaction move forward. But too much acid or too warm, and unwanted side reactions kick in, producing phenol instead of the diazonium salt, like an overexcited crowd ruining a chemistry concert. To prevent this, chemists use buffers or carefully control acid addition, keeping pH just right, like Goldilocks porridge. Imagine a temperature versus yield graph showing a sharp peak at low temperatures and a lab setup with an ice bath holding your reaction flask. This is your chemical safe space. Controlling these conditions is the key to efficient, clean diazonium salt formation. Time for some number crunching. Imagine you have 5.6 grams of aniline, which is C6H5NH2, with a molar mass of 93 grams per mole. The question, how much sodium nitrite, number 2 do you need to fully react with this amount? Our reaction is aniline plus sodium nitrite plus 2 hydrochloric acids forms benzene diazonium chloride plus sodium chloride plus water. To solve this, first calculate moles of aniline. 5.6 grams divided by 93 grams per mole equals about 0.06 moles. Since the reaction is 1:1 between aniline and sodium nitrite, we'll need 0.06 moles of sodium nitrite. Now, sodium nitrite weighs 69 grams per mole, so multiply 0.06 moles by 69 grams. That gives you approximately 4.14 grams of sodium nitrite needed. Picture a bar chart showing equal heights for moles of aniline and sodium nitrite, then a conversion arrow turning moles into grams, chemistry in numbers. So, next time you prep diazonium salts, you know your math is as solid as your flask. Let's see where our superstar diazonium salts show off in the real world. These salts serve as key intermediates, making phenols, azo dyes, halogenated aromatic compounds, and iodine derivatives. The famous Sanmia and Gattermann reactions use diazonium salts to swap out groups for chlorine, bromine, or cyanide, kind of like a chemical swap meet. Plus, coupling reactions between diazonium salts and phenols or other aromatic amines form azo dyes, the bright, colorful patterns you see on textiles and artworks. These reactions are also handy in analytical chemistry. Yes, the same salts help detect aromatic primary amines by changing colors in the test tube, making chemists smile. Imagine a pathway map where diazonium salts lead off into phenol on one branch, azo dyes in the middle, and halogenated derivatives on another, showing just how versatile these molecules really are. Chemicals that do so many jobs deserve a medal, don't they? Now, a word of caution. Diazonium salts are high maintenance. They're only stable when cold in aqueous solutions. Above 5 degrees Celsius, they start breaking down, releasing nitrogen gas, which can be dangerous. And if you think about isolating dry diazonium salts, forget it. They're explosive, like fireworks waiting to happen, so they must never be stored dry or isolated. Instead, chemists generate them fresh in the lab and use immediately. Some special diazonium salts, for example those with tetrafluoride as the anion, are more stable and can be isolated as crystalline solids, but those are exceptions, not the rule. Picture a stability chart rising steeply up to 5 degrees then dropping quickly with flashing warning symbols to remind you, handle with care. Safely handling these compounds is a must for any chemist because safety always comes first. Let's wrap it up. To prepare diazonium salts, aromatic amines react with sodium nitrite and twice the amount of acid, giving aromatic diazonium salts plus sodium halide plus water. Remember, sodium nitrite plus acid makes nitrous acid plus sodium salt, with nitrous acid sitting behind as the key reactant. Diazonium salts don't like heat. They're unstable above 5 degrees Celsius and always prepared in situ, meaning on the spot, under cold, acidic conditions. And the true star of the show is the nitrosonium ion, formed from nitrous acid in acidic medium, which actually does the magic of diazotization. So, that's the story of making diazonium salts unstable but utterly indispensable in aromatic chemistry. Chemistry really is fun, especially when you can laugh and learn. Until next time, keep exploring.